Hello, welcome to lecture 11. So today we talk about the large-scale training techniques for AI models. Let me introduce the work of also AI, which is a work led by Professor James Demo and me. So the key techniques in also AI actually are very general. So even you use other systems like DeepSpeed, Electron, or PyDBT, or some future software, they should use similar techniques. So this topic for this lecture, we just introduce the techniques, the methods, the approaches. You can use these approaches for different implementations. Okay. So here is the outline for today's topic. Firstly, let me briefly review the challenge and opportunity in the large AI model age. And the second part, let me introduce the key techniques. Actually, it's just n-dimensional parallel laser. Because today, you probably heard the news OpenAI is using 25,000 GPUs to train their AI models. 25,000 GPUs. Each GPU also has hundreds or even thousands of threads. So you have so many processors. You need a very high power. You need to make sure each processor, all the processors, full. You give them enough food, otherwise they will be hungry. So the GPU utilization very, very low. So that's why we need an n-dimensional power laser. And so even GPU is very powerful, however, we still need to improve the memory efficiency because we don't have enough memory for the large AI models like GPT-4. And then I introduce some performance within the platform. So the key idea as the algorithm techniques. So firstly, let me give you a figure. For this figure, the horizontal axis is a timeline. The vertical axis is a number of parameters in AI models. So we talk about GPT, BERT, transformer, ResNet, and also solution transformer in this lecture. So here is just a summary. You see, from June of 2016 to June of 2021, so the model size increased from here, roughly 20 million parameters. Here's the 20 million. Here, GPT-3 is roughly 20 billion, 170 roughly 20 billion. Actually, 10,000 times larger than ResNet. And the solution transformer powered by Nature of Experts (MOE) also 10 times larger than GPT-3. So this solution transformer actually is 100,000 times larger than ResNet. You see, just 5 years, 100,000 times larger. That's very crazy. So for every 18 months, actually, the model can increase us by 40 times. For the year between 2018 and 2021, they increased 340 times for every 18 months. So that's why we need to redefine the software, redefine the infrastructure to handle this model training, fine-tuning, deployment. So the techniques behind the infrastructure for large AI model is high performance computing. So for high performance computing, basically, we want to do whatever possible to make the GPUs or CPUs or TPUs or NPUs faster, more efficient, and also hopefully cheaper. So now I just give you some information about the growth rate of a large AI model by number of parameters. So, but because this is a summary of the training, let me also explain. So why do we believe large AI model? Firstly, as we know, large AI model can give us better performance. So today you use GPT-3, you use GPT-4. Clearly, you can feel the difference. GPT-4 should be much better than BERT. BERT is only 300 million parameters. GPT-3 has 175 billion parameters. And you have a larger model, you get better performance. The model has a higher level of intelligence. That's the key reason. So why we want to larger model. And another interesting trend is even for the researchers or small enterprises, they use small model or tiny model. So the definition of small model is also becoming larger. So you see here around XSA time. That's the definition of a small model. So for example, in 2015, the small model is like that. In 2017, the small model may be ResMap. So today, maybe the small model just like Llama 7B, like Llama 7 building. So today, you see, even for the small model has 7 billion parameters, which is roughly 20 times or 30 times larger than the largest model in 2018. The largest model in 2018 is BERT, which has 300 million. So the definition of a small model is also becoming larger. Small models are also growing exponentially. That's why do we believe large model in next 3 or 5 years. But I believe eventually they are going to flat because we just cannot keep scaling the machines. Today, 25,000 GPUs. Maybe 3 years later, we have 100,000 GPUs. But eventually, we have to stop. But we don't have enough energy. Energy cost is so high. But in the next few years, like 3 or 5 years, we can still grow the model. Hopefully, GPT-7 or GPT-9, we can get the best model. And also, for the next 3 or 5 years, I think one interesting point is the hardware actually is becoming cheaper. So here, by cheaper, I mean the T-flops per dollar. You give me $1, how many T-flops I can give you? So, for example, you can check the price for H100 GPUs, the price for A100 GPUs, the price for V100 GPUs. You also know the peak performance of this GPU, right? Just use the peak performance divided by the price. That's the T-flops per dollar. Actually, from year 2015 to 2020, they increased 45 times. That means our hardware is becoming cheaper or more efficient. So as the hardware is becoming cheaper and we can make full use of this hardware performance, we predict sharing my screen. So we predict we should be able to reduce the training cost of GB3 from $3 million in 2020 to just 70,000 in 2025, or maybe just $10,000 because we may have faster algorithm. So here is just making full use of hardware, but we may have better model, faster algorithm. Probably it can be just $10,000 US to 20B3 in 2026. Okay. Yeah. So that's why we believe. So here we can do something to make a full use of the GPU hardware or similar like a TPU. Yeah. Okay. That's a brief motivation for the techniques related to machine learning system or HPC AI, high performance computing for AI. So going back to the challenge, now let me give you some information, give you some data. So to here, I just want to highlight why it's so expensive. Let me just use a PaLM model. PaLM is a very big model introduced by Google. PaLM has 540 billion parameters, roughly 3 times larger than GPT-3, but it's still smaller than GPT-4. So how about we assume we can use some magic compression techniques to feed the PaLM in just in one GPU. How about we just assume this is possible? So even we can feed to one GPU, so the training for one GPU is 300 years to training this model. You use one GPU to train it as possible. We hope it's possible, but it's 300 years. It's not meaningful. That's why we need thousands of, even tens of thousands of GPUs to train these models. And so even we have tens of thousands of GPUs, it's also very expensive. And we just run the GPU, run the training once, cost is $9 million. So that's why it's very challenging to train and deploy these models. So there's a lot of work we needed to do to make it faster, cheaper, and more efficient. That's the motivation for today. Any questions so far? Yeah. So let me give you an overview of causal AI. So the idea of causal AI actually is very similar to something like deep speed Magnetron, or I think maybe in the future advanced PyTorch. So we want to build a better high-performance computing techniques, make the training more efficient. So what kind of techniques do we need? I believe at least we need three layers of implementation. So the first layer is efficient memory system. So why should we care about the memory system? I hope you still remember the quiz. So to compute the memory cost for training AI model, training GPT-3, how about roughly 20 billion parameters? Roughly 20 billion parameters. Sorry, 200 billion. 200 billion parameters. So which means GP3 has 200 multiplied by 10 power, 10 to the power of 9. So how about we just use a single precision? So each precision, each parameter is 4 bytes, 4 bytes. So in total, we need 4 multiplied by 200. All right, I should write it down. So the GP3 has roughly 200 billion, and that's 200 multiplied by 10 to the power of 9 parameters. How about we use single precision 32? That means single precision. Single precision. So for each parameter, it's 4 bytes. 4 bytes. 4 bytes. So you see, now we need 800 GB. Right? G is 10 to the power of 9. So for just a parameter, right? We know we also have the gradient, gradient, right? For atom or matter, we need first momentum, second momentum. That's just a model. It's also 800 GB, 800 GB, 800 GB. That's also 800 GB. And also we have something like activation. It's also roughly 800 GB. How about we just ignore it? So you see for here, we just want to load the training load memory. We need a 300 TB memory. 300 TB, right? So we know for H100 GPU, H100 GPU, one GPU only has 80 GB memory. So you see, that's so crazy. So we just load the training code. We need 3 TB memory, but a single H100 GPU only have 80 GB memory. That's why we care about the efficient memory system. And also, the second layer of implementation, we should design better or more scalable algorithm for parallel computing. But we have to use some of at least 1,000 GPUs. We need a very high algorithm. And also to make sure our algorithm is very scalable, we need to light scale optimization. That's why at least we need a 3 level of implementations. And as we know, for the high level framework, we have different options. Like most of our students are using technology. But in the future, we maybe use something different like Lightning or even Newton flow. And also, in the low level, we have different hardware. Different hardware like CPU, GPU, TPU, IPGA. So I last week I talked to the CEO of a startup. So he is trying to use IPGA to train the model. We don't know what's the future. Maybe it's also possible. So that's why we need a new software or new implementation to make sure we have a high performance, high efficiency, and also hopefully it's cheap. So by the way, I also briefly go over. So if we can implement the techniques very efficiently, we can make the software very popular. Like ClassOI already got more than 30,000 start on GitHub. It's actually fast, even faster on the traditional software like Spark, DOS-only. Yeah. So also I also have many users and developers over the world. So here is a map of my GitHub Sparks. Well, I just skip this part and go to the technical parts. So now, let me firstly talk about the n-dimensional parallelism system. So for n-dimensionally, basically the idea is to partition the computation. So how can we partition the computation? We know it's just forward pass layer by layer, backward pass layer by layer. So the first dimension is we have so many layers. Can we do something like a pipeline? Like we have 50 layers. Can we just partition them to 50 parts? Unfortunately, the answer is no. Because for different layer, forward pass, backward pass, they are depending on each other, right? We finish the computation for first layer, and then we do second, and then we do number 3, then we do number 4, then we do number 5. Forward pass layer by layer. So for here, the only thing we can do is to build multiple different pipes. So like different pipes which means different data batch. So the first micro batch is computing the layer 1. The second batch computing layer 2. Number 3 batch computing layer 3. The idea of pipeline algorithm is something like this. Build a different micro batch. Different micro batch cover different layers at the same time. And the second part is the tensor parallelism. So here the idea is, can we partition the computation within each layer? Right. So there's something very interesting. Probably, I hope you understand the interesting part. So like ResNet 50, ResNet 50 has roughly 20 million parameters. ResNet 50 roughly has 20 million parameters. GPT-3 roughly has 200 billion parameters. So you see, GPT-3 is 10,000 times larger. 10,000 times larger. 10,000 times larger than ResNet. But for ResNet, this one has 50 layers. This one, I think, has upper bound is 100 layers. So only roughly 2 times larger. You see, the number parameter is 10,000 times larger, but the number of layers is only two times, which means the layer is becoming wider. So that means each layer is more expensive, more computationally expensive. That's why we believe we should partition the computation within each layer. So that's tensor parallelism. So for tensor parallelism, within each layer, it's just a matrix multiplication, right? So the key idea here is how can we efficiently partition this matrix multiplication horizontally or vertically or even 2D, 3D. Let me introduce the detail later. You see, that's doing partition computation across different layers. That's partition the computation within each layer. And also, let me also introduce sequence parallelism. I hope you remember last lecture, the open source. For each video, we have roughly 1.2 million tokens, 1.2 million tokens, which means the sequence length is 1.2 million. So long sequence, the memory overhead is very high. So how can we make sure it's not out of memory? We need a partition sequence to make sure it can work very well for training. So as a second parallel, so at least we need these different layout parallels. Make sure each GPU is fully utilized. And the most fundamental approach is data parallelism, which means we have a bunch of data, we just partition them to different parts. Each server or each GPU just handle one part. Just the traditional approach. But here the idea is how can we maximize the insights. That's the key idea for parallel computing in machine learning. Now, let me introduce the first approach, data parallelism first. So the idea of data parallelism, I think is very easy to understand. We have a bunch of data. So assume now here, how about it's just 6. We have 6 data samples. We have 3 servers or 3 machines. We partition these 6 data samples to 3 machines each. Each server or each GPU has 2 data points, right? 2 images here. So each GPU actually compute the local gradients. 2 4 parts, 5 parts, the local gradients. And the GPU also got its local gradients. And then we do an average to get the global gradients. And then we just send the global gradients to each server to update, or we can just update here and then send back to the new weights to all the GPUs. See, that's just the data parallelism. Any questions? So if you do not have question, let me ask you a question. So do you think assume the number of iterations into T. So how many communication messages here? How about the number of iterations is T? So how many communication messages here? Anyone want to share your answer? Yeah, please.
Maybe T times model size times 2.
T time model size?
Model size. Racks, total racks.
Sorry, can you
total devices.
Total devices.
Times 2.
Times 2. Why?
Why? One for gradient, one for model, and this need to be broadcast to every rack.
Okay, so why you multiply by the number of devices?
Because you need to receive every gradient from every rank, and you also need to broadcast the new model parameters to each rank.
Okay. Yeah. So I believe your answer is just 2 times pt, right? Your answer is this. P is the number of devices.
Yeah.
Okay. Okay. Anyone has a different answer? Yeah. So I think this answer is correct, but do you have a better algorithm? Do you think can you reduce this number? Your answer is correct. Do you have a better algorithm?
Maybe not.
Okay. Yeah. I believe like you can search. I hope we can got what PT. PT. I feel like you after class you can search or reduce operation. So you see, here for data power laser is it is highly efficient. It's highly efficient, right? So we just needed to do the average operations each iteration. It's just a single communication message by something like or reduce. So this approach actually highly efficient for parallelism. So, but the concern of data parallelism is I will increase the base size to very large, reduce accuracy. So here, the idea of to make the base size very large is to increase the base size by k times. We also reduce the number of iterations by k times because we want to keep the number of epochs. Do you remember the definition of epoch? Remember? Anyone still remember the definition of epoch? Do you remember the definition of epoch? Okay. Does the TA remember the definition of epoch?
After a training of one epoch data means that you have trained all the batches.
Okay. Yeah. Yeah. So the idea is you touch the data set once. Yeah. Let me replace the number of epoch. That's actually very important definition. Epoch. For example, in total you have 10,000 samples. The data set is so large, 10,000 samples. Your base size is 100, which means every iteration you just touch 100 samples. So which means you need 1,000 iterations. You need 1,000 iterations to finish one epoch. That's your data set. So your data set has 100,000 samples. The base size is 100, which means you need 1,000 iterations to touch all the data set. That's the definition of one epoch. So for here, the idea is we increase the base size by 2. How about we increase the base size by 2? we increase base size by 2. And then we just need 500 information. We increase base size by 2. One epoch, we just need 250 iterations. So that means we want to maximize the base size. To maximize base size, assume we have enough GPUs. So, but the concern is, you see, even we train the same number of epochs, we are losing accuracy. So the blue line here, like base size of 100. The black line by star is a base size maybe 10,000. See, even they train the same number of epochs, but this guy, the black line, has much fewer number of iterations. That's why its accuracy is lower. By the way, I want to ask you a question. So, how about this one and this one? That's the first one and second one. Do they have the same number of floating point operations? This guy and this guy. Do they have the same number of floating point operations? No, why?
I think if the batch size is larger, then the number of times the gradients get back propagated in the model will be less.
No, floating point operations, number of operations.
The same?
Yes, they're the same, right? They have the same number of floating point operations. Because for here, every iterations you compute for 100 samples. But for here, every iteration you compute 400 samples. Actually, you just addition them to 100. Right? It's this one is equal 100, 100, 100, 100. Right? If you like, you can still compute them sequentially. So they have the same number of floating point operations. Okay, please remember, if you fix the number of epochs, means you fix the number of floating point operations. If you fix the number of, if you can fix the number of epochs, you are fixing the number of floating point operations. Any question for this? Yeah, please.
But aren't there like operations that's related to the batch, like the mean of a batch?
Actually, it's
very, very small.
the mean of batch.
Yeah. Like if you want to aggregate the gradients across one batch.
Oh, okay, yeah. Let me, yeah, so that's a minor cost.
Okay.
Because to the average, it's all in fact. Okay. So we know the cost of our pass, vector pass is O n cube. The average just O n. It's a minor cost. Yeah. But it's a good point. Also, you see here, so we increase the number of increase the base size by 10 times. We are reducing the number of iterations by 10 times. So for here, actually, we are also reducing the communication messages by 10 times. See? So light batch is more communication efficient. Okay. So now the question is how can we make sure they get the same accuracy? So firstly, let me explain why they get different accuracy. So here is a figure from Intel's paper. So according to Intel, because light batch training is a sharp minimum problem, so which means even we can train the model very well, we cannot get good testing accuracy. It's very hard to generalize. Because light batch training is sharp minimum, so you see the training loss is low, but the testing loss is very high. For small batch, it's a flat minimum, which means the training loss is low, the testing loss also low. So that's why we designed some algorithm like burst and lamp. So here, to my details, I'm going to skip the algorithm part. The idea is to make a light batch training get the same accuracy. You see, even for this so traditional algorithm, you have a lot of work to do. You need to understand what's the benefits here, what's the trade-off. So why is not efficient, and what we can do to make it work. So firstly, the benefit, the light batch training and reduce the making cost, make your algorithm to fully utilize the more solvers. But trade-off is they lose accuracy. How can we keep the accuracy? We need a new algorithm, new light scale provider like loss and that. That way, our RTA also designed a different algorithm to make light batch training better. If you are interested in this, you can talk to me, RTA. So here, let me show you after assume we can get the same accuracy. Assume these lines get the same accuracy. Now let me show you the performance. You see, we increase number of GPUs. We also increase the base size. We can reduce the Vein transformer training time from 73 hours to roughly 14 minutes. So you see, we almost get a very perfect scaling. Okay. So now let me talk to the second part, the tensor algorithm on the pipeline algorithm. It's actually the professional name is model parallelism. So why is model parallelism? Because for data parallelism, actually we just touch the data. We do not partition the model. We do not touch the model, which means for data parallelism, each device has a copy of the model. But we do not touch, we do not partition model here for data parallelism. Each device actually has a whole copy of them. But for here, model parallelism, we want to partition the model, partition within the layer, partition across different layers. That's the idea for model parallelism. So for model parallelism, let me firstly talk about microfile introduced by NVIDIA. So you see the idea here is just partition the computation within each layer. So within each layer, so here is the example of our class. I think vector class the idea is similar. Within each layer, it's just matrix multiplication or class matrix multiplication. Now, how about we just send our data in X here. So for matrix multiplication, I think we can partition them horizontally or vertically. So how about let me write another example to give you a better understanding. Well, now we have first matrix is 4K by 2 million or what? 4K by 2 million. So the second matrix is 2 million by 108. Right. So now we have 4 devices. We have 1, 2, 3, 4 devices. We have four devices. We know if we have 1 devices, it's just something like this, right? That's 4K by 2 million. It's what the 4K by 2 million. That's million by 128. Something like this. And after computation, we know the result is 4K by 128. Now, how can we partition this computation? Anyone has an idea? Or how can we partition? Should we partition horizontally or vertically? We have four solvers. 4 solvers. Well, let me introduce the first solution. So how about we partition this guy? Now, for each solver, we had 1K by 2 million, 2 million by 128, and also 1K by 2 million, 2 million by 128. Also here is 1K by 2 million, 2 million by 128, and the same 1K by 2 million, 2 million, 128. Now, after the computation, we know the results for the first one is just 1K by 128, right? It's that's the first matrix, second matrix, right? The result should be 1K by 128. This is also 1K by 108. 1K by 108. 1K by 108. Okay. Now we have 1K by 108. But our result should be something like this: 4K by 108. How about we just gather them together? Let's gather operation. Now it's about 1K by 108, 1K by 108, 1K by 108, 1K by 108. That's 1K. Sorry, that's 108. 100. Sorry, I think it's wrong. It should be not this way. That's wrong. I think it should be something like this. However, that's 1K by 128. That's 1K by 128. And the second one should be also this way. Number 3 also by this way. Number 4 also by this way. Right. That's 4K. That's 1K. 1K. Okay. So the results also 4K by 100. That's basically the tensor parallel answer. You how to partition the computation to different servers. Now let's take a look. So if we have a single server, this computation on a single server, do you still remember the floating point operation for matrix expression multiplication? So how many floating point operation for this? Anyone knows? So you have M by K matrix multiplied by K by M matrix. So number of operations should be 2 times MKN. 2 times M by MM. Okay. The number of floating point operations. So basically, it's add a pass. Add pass operation. Multiply that. Basically, for each element, it's multiply and 2 operations, right? Because you need to multiply them together. Yeah. So you see, for here, the number of floating point operations should be 2 times 4K by 2 million by 108. Right? That's 16 by 108 billion. Right? That's 2 trillion. Right? So for this, we have 2 trillion operations. How about for here? on each solver, this is just 1K by 2 million by 120. So each solver we have that's 206 billion multiplied by 2. That's 500 billion operations. On each solver we have 500 billion operations. Clearly equal to 2t over 4. Or equals 2t over 4. So that's just the idea for tensor parallelism. Clearly, for tensor parallelism, we do not increase the number of floating point operations. We do not. The cost here is a gather operation. We need to put them together. But for computation, it's minor, but we have a communication cost. By the way, if you like, you can also partition this guy. I also partition this guy. If you partition that guy, should be let me write a different solution. You can also partition that one. I think that guy, first one is still 4K by 2 million. That's 2 million by 32. 32. But now we partition the column dimension of the second one. That's also 4K by 2 million. 2 million by 32. 4K by 2 million. 2 million by 32. 4K. 4K by 2 million. 2 million by 32. So after the metric computation, you see for the result for this is 4K by 32. 4K. 4K by 32. 4K by 32. 4K by 32. 4K by 32. Now, 4K by 32, I think it is something like this. We put them together, 4K by 32. 4K by 32. It's running 4K. This is 32. Yeah, so it's still 4K by 120. Okay. That's the idea of a tensor parallelism. Any question for this? By the way, I want to ask you a question. So we just partition this one, partition by this one. Can we partition this one? Partition the 2 million dimension. Can we partition the 2 million dimension? Anyone wants to share your answer? So how about let me give you a visualization. Probably you have a better understanding. Can we partition the 2 million dimension? So the 2 million dimension actually is here. Right? How about we just divide 4K by 2 million? Partition this by 4 parts. Partition this one by 4 parts. So we use this one multiplied by this one multiplied by this one multiplied by this one multiplied by this one. So now you see, so for if we do it together, no partitioning, we actually should be sum them together, right? The ideal matrix, right? And you use this zero multiplied by this column, and then you sum them together. So now you want to do partition. How about we first do this one with this one, and sum them together. This one and this one, we sum them together. This one and this one also sum them together. And also number 4 and number 4, we sum them together. So that's possible. So we just need to sum them together. We shall be okay. Our let's partition the number 2 dimension. So that's 4K by 2 million, which means we partition them by 4K by 500 4K. So partition this is 500K by 128. That's 4K by 500 about 500K 500K 128. This one the same. Okay. 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 Also 4K 500 by 120. Right. So now every server or every device we do a matrix multiplication is the result is 4K by 128. 4K by 128. 4K by 128. 4K by 128. But I use this one multiplied by this one. The result is 4K by 128. So now we just sum them together. Sum them together. Sum them together. It's a sum. It's also 4K by 128. You see the same thing here. Okay, down here. Now the number of operation for this solution is roughly 500 billion operations. How about for this one? It's 4K by 100K by 128 multiplied by 2. The number of floating point operation on each server. And just do a simple math. So that's 8 by 500 million. KK is million. Divided by 128 equal to 128 by 1K is equal to 128 by 3. So the same here and here. The number of floating point operations are blocks. That's also blocks. Okay. You see, at least we have those 3 solutions, but every solutions we do not increase the floating point operation. That's very important. Otherwise, our algorithm is not efficient. If we use more solver, our floating point operation also increasing. That can be a major cost. See, any question for this? That's actually the key part of this lecture. Any question for this? Okay, good. Yeah. So that's the second part. Basically, we just use a 1D approach. So you partition this, partition this. I think you see idea of partitioning this here horizontally. Partitioning this very quickly. Partitioning this actually is also vertical. It's a 1D. It's a 1D approach. So later, if you like, you can also check 2D, 3D, and like you can check possibly adding information. Basically, we can be more aggressive to put them into block by block, more complicated scheduling approach to get the results. So here is just idea for 1D, 2D, and 5D. So for this lecture, we just focus on 1D. So actually, for today, probably 1D is enough. Like you can check Metron, deep speed, even you train the model like GPT-3 or OpenAI, they mostly use the 1D approach. The idea is just find vectors. Yeah. Now, the number 3 part, as I mentioned, is the long sequence is coming. Have you heard of data of AI uniform astronomy? They claim that they support the sequence length of 1 million. And open source guys, they support the sequence length 1.2 million. I think in the future, probably we may need 100 million or even 1 billion tokens. That's also possible. We know the loss function of the GPT. In the loss function of GPT, I hope you remember. We use the context information to predict the next word. That means a longer sequence gives the model more information to make the prediction. More information basically means a better decision. So that's why long context is important and give us better accuracy. Please try to remember the loss function of GPT, like context length information to predict the next token. That's why longer context we get a better accuracy. But now you see the concern is memory. And you still remember the key operation for transformer is the QPV. Like we use the first token's Q or P to match the QP matches each other, and then we compute the attention score. So that means more tokens, we need more attention scores. The memory overhead is exponentially after some point. So the required memory, you see. So as I just gave you the results for the memory cost with gradients, first moment, second moment, and or neither. This is already a lot for the model like GPT-3. But now we have additional cost from the long sequence that can be created. So the idea here is we cannot put the whole sequence to a single server. Like we have source for server, we cannot put the whole sequence here. We also have to partition the sequence. We also need to partition the sequence. Because otherwise the memory cost is too high. So now, how can we partition the sequence? Like we have 4 GPUs here. B image size, H means hidden dimension. So how about the sequence length? For each GPU, we just partition them by 4. Well, we have 4 GPU. We have P GPU, partition them by P. Now, how can we do that? The idea here is we should minimize the communication. Because I partition the sequence, so here, now this sequence has 1K tokens. So here, 1K divided by 4 is 156. I got the token from here, token key, to match this one. And also get token here to match the parity of this one to match the key here to here. Which means all the GPU need to talk to each other. The communication cost is P squared. P is number of GPUs. Too high. That's not efficient. How about we use the rim-based server attention? Basically, the idea is, firstly, we have a Q and a P to compute the attention score. Now, for next step, I need to get a new key because I need to match a new token to compute the attention score to a new token. To get a new key from my left-hand side neighbor to send all the key my right-hand side neighbor, and then compute the second attention score. Next step, also get a new key and send all the key to our right-hand side neighbor to compute the number 3 attention score. and then number 4 again is gone. So in this way, we can finish everything. So you see the communication overhead for this just p minus 1. So the naive or the baseline is p squared message. So here just p minus 1 as p is number of GPU. You see, after we partition the sequence length, now we can use a larger byte size. We can also get a higher throughput. So we can also use a longer sequence. Because otherwise it's an out of memory. So now the final part of the technical part is efficient memory system. So that's today's GPU software architecture. We have the GPU memory, have the CPU memory, and also NVMe memory. So here it's a very interesting. So GPU memory actually we only have like 100 GB, roughly 100 GB, but CPU memory is much larger. NVMe memory also much larger. So the question is, can we upload some data from GPU to CPU and then from CPU to NVMe? So the idea I think is good, but the concern here is the data movement costs from GPU to CPU is very high. The data movement from CPU to disk is even higher. Let me give an example. So you do a computation here, just like you have a meeting in Singapore. You move the data to CPU, you have a meeting in Malaysia. You do a data movement in the NVMe disk, just like you have a meeting in New York. So we can use larger memory space, but the cost is much higher, 10 times, 100 times higher. So the idea here is how can we make full use of this memory and also minimize the data movement between CPU memory and GPU memory, and also between GPU memory to NVMe to minimize the data movement amount and also minimize the communication frequency. So there are some existing solutions like Zero. Basically, they just partition them, but they do not use CPU GPU memory very efficiently. So here, I think the idea is we should build a tensor chunk mapper. The idea is we use this tensor chunk mapper to know which part of the tensor is not active. It's just like something to make prediction, it's not active. And it's highly inactive. For example, for next 50 iterations, we can move them to CPU. And we should to build a stable tensor list to rank them by they are active or not active. And then we move them to NVMe or CPU memory. That's the key idea. Okay. So by doing so, we can make a full use of the CPU memory and NVMe memory. We can use the same GPU to handle a much larger model. Because now we can use CPU and NVMe at the same time to roughly slower. So it's definitely slower because we need more data to CPU memory and NVMe. But the key idea is we can train 20 times larger models. So here, the 3 times faster means you do not use this kind of techniques. You just manually upload them. It's very slow. We need to control the frequency to minimize the data movement between CPU and GPU, between CPU and NVMe. Compared to this side, it's still faster. So I think I have finished all the technical parts for the parallel machine learning, large-scale AI techniques. Any questions so far? So yeah, I feel like you can check the total class by different open source after a class. So any questions so far? Okay, good. Yeah, so this is our final lecture of this semester. So if you have any questions, you can contact me later. I mean, we also have office hour. You can also reach me to the TAs. Yeah, so because this is the final lecture, so I ordered some desserts for you. Our TA can like you can have the desserts. Thank you so much. That's it. Do we have a tutorial?
Yeah.
Okay, yeah. How about come back screen, please? Yes, you are.